Age of aluminum, industrial expansion, commercial revolution, and global market dynamics, 1945 to 1990. The history of aluminum in the second half of the 20th century represents one of the most profound material transformations in the history of global industry. Prior to the outbreak of the Second World War, aluminum was largely a specialty material, prized for its exceptionally low density and high electrical conductivity, but severely restricted in its commercial application by the immense financial and energetic costs of extraction and refining. Following the 1886 discovery of the Hall-Héroult refining process by Charles Martin Hall, which dramatically reduced the cost of extracting the metal from its ore, aluminum slowly began to make inroads into consumer goods, but it remained largely absent from heavy industry. The crucible of global conflict, however, catalyzed an unprecedented expansion in production capacity that would forever alter the material's trajectory. The insatiable material demands of modern aviation warfare dictated that aluminum become the absolute structural backbone of the military-industrial complex. To illustrate the scale of this demand, a single B-29 Superfortress bomber required approximately 50,000 pounds of aluminum, a mass that comprised fully two-thirds of the aircraft's entire gross weight. Between the outbreak of the war in 1939 and its peak industrial output in 1943, primary aluminum production in the United States alone skyrocketed from 149,000 tons to an astonishing 835,000 tons, effectively doubling the nation's share of global output from 21% to 43%. To meet this extraordinary demand, the United States government collaborated closely with the existing aluminum industry to design, finance, and construct more than 50 new aluminum production and fabrication plants across the country. Globally, the sheer volume of aluminum mobilized for the war effort was staggering. The Soviet Union, for instance, received 328,100 metric tons of aluminum from its co-combatants between 1941 and 1945, a critical supply line without which the output of the Soviet aircraft industry would have plummeted by more than half. When the war finally ended in 1945, the global aluminum industry faced a sudden, severe, and potentially catastrophic crisis of overcapacity. The massive factories and sprawling smelters that had tirelessly churned out metal for fighter planes and heavy bombers were abruptly left without their primary consumer, forcing the industry to pivot aggressively toward civilian and commercial markets to survive. This post-war pivot initiated a half-century of relentless innovation, sweeping market restructuring, and fierce commercialization. Between 1945 and 1990, aluminum successfully transitioned from a strategic military reserve material into a ubiquitous mass consumer good and an essential structural component of the modern world. This transformation was not merely a story of steady metallurgical advancement, but rather a complex, multi-layered interplay of landmark antitrust litigation, shifting geopolitical supply chains, the eventual financialization of global commodities, and a fierce, decades-long marketing war against deeply entrenched traditional materials like steel, iron, and glass. Through the revolutionary development of the two-piece beverage can, the architectural implementation of the towering glass and metal curtain wall, the systemic lightweighting of the global automotive industry, and the extreme engineering demands of Cold War aerospace, aluminum fundamentally reshaped the physical and economic landscape of the 20th century. Antitrust litigation and the fall of the Alcoa monopoly. The commercial trajectory of aluminum after 1945 cannot be properly understood without first examining the radical government-mandated restructuring of the industry's corporate landscape. For the entire first half of the 20th century, the American aluminum market was fundamentally a pure monopoly controlled by the Aluminum Company of America, globally known as Alcoa. Protected by its early patents on the Hall-Héroult refining process, and fortified over decades by a vast, impenetrable network of vertically integrated supply chains spanning from tropical bauxite mines to domestic rolling mills. Alcoa was the sole legal supplier of primary aluminum in the United States until the onset of the Second World War. However, this absolute dominance made the corporation a prime and inevitable target for federal antitrust regulators. The legal battle that dismantled this monopoly began in 1937 when the United States Department of Justice filed a massive antitrust lawsuit bringing over 140 specific charges against Alcoa, accusing the corporate giant of monopolizing 16 different markets and actively conspiring with foreign producers to prevent them from entering the lucrative American market. The litigation dragged on for years, surviving wartime delays and intense corporate lobbying. Finally, in a landmark 1945 ruling, Judge Learned Hand of the United States Court of Appeals for the Second Circuit determined that Alcoa's overwhelming 90% market share of the virgin aluminum ingot market constituted an illegal monopoly under the Sherman Antitrust Act. In a decision that would reverberate through American corporate law for decades, Judge Hand argued that the mere possession of the power to control prices and curb competition was inherently monopolistic and illegal per se, deliberately disregarding Alcoa's defense that it had acquired its position honestly through greater industrial efficiencies and without necessarily engaging in overtly predatory practices. Furthermore, the court ordered injunctions against Alcoa to prevent the resumption of an illegal price squeeze that the company had utilized to force out competing manufacturers of aluminum sheet metal. The ultimate resolution of the Alcoa monopoly was deeply and inexorably intertwined with the post-war disposition of the government's wartime assets. As the war concluded, the federal government possessed dozens of advanced aluminum production plants that it had financed to supply the military. Recognizing a unique opportunity to artificially engineer a competitive domestic market, the Federal Surplus Property Board deliberately sold or leased these government-financed alumina and smelting facilities at highly favorable terms to new market entrants. The primary beneficiaries of this government-sponsored market creation were Reynolds Metals and Kaiser Aluminum. Reynolds Metals, founded in 1919 by Richard Reynolds, initially to manufacture tin and aluminum foil wrappings for the R.J. Reynolds Tobacco Company, seized upon this opportunity to transform itself into a primary metal producer. During the war, Richard Reynolds had leveraged his assets to secure government loans to build reduction plants in Alabama and Washington. After the war, the company leased and eventually purchased the massive government-built Hurricane Creek alumina plant in Bauxite, Arkansas, which boasted a yearly capacity of over 1.5 billion pounds of alumina, making it the largest facility of its kind in the world at the time. Kaiser Aluminum similarly acquired critical smelting infrastructure in Spokane and Tacoma, Washington. As part of the antitrust settlement, Alcoa was legally compelled to license its critical, closely guarded alumina production technology to these new market entrants on a royalty-free basis, effectively subsidizing their entry into the market. Additionally, Alcoa's formidable Canadian counterpart, Alcan, which had originally been established as the Northern Aluminum Company in 1901 before formally detaching from Alcoa in 1928, was definitively and legally spun off by a 1950 court ruling, ensuring it would act as an independent competitor rather than an international subsidiary. Alcoa attempted to use the government's creation of Reynolds and Kaiser to argue in court that the monopoly problem had effectively solved itself, thereby successfully avoiding a complete corporate dissolution in a historic 1950 district verdict. Nevertheless, the company irrevocably lost its absolute ironclad hold on the American market. Over the subsequent years, Alcoa watched its domestic market share plummet from nearly 100% to approximately 1/3. Rise of the six majors and the new oligopoly. This forced divestiture transitioned the global aluminum industry from a unilateral monopoly into a tightly coordinated oligopoly. Throughout the 1950s and 1960s, the global market came to be overwhelmingly dominated by a group of multinational corporations collectively referred to as the Six Majors: Alcoa, Alcan, the rebranded Aluminum Limited, Reynolds, Kaiser, the French firm Pechiney, and the Swiss corporation Alusuisse. Together, these vertically integrated giants controlled between 70 and 80% of the free world's aluminum market by 1960. Despite the loss of its monopoly, Alcoa remained highly profitable because overall consumption of aluminum doubled during the 1950s, spurred by the Korean War and the aggressive discovery of over 2,000 novel civilian uses for the metal. The intense competition among the newly minted American giants became the high-octane engine for the aggressive development of these new civilian applications. Each firm deployed massive advertising budgets, developed sophisticated research laboratories, and sought to capture market share in an expanding peacetime economy. The geopolitics of bauxite and trans-imperial supply chains. The physical structure of this post-war corporate oligopoly was firmly anchored by a complex, geographically disparate global supply chain. The production of usable aluminum is a two-stage process. First, bauxite ore is extracted and refined into a white powder called alumina using the chemical Bayer process. Second, the alumina is transported to a smelter where it is subjected to the Hall-Héroult electrolytic process, passing massive electrical currents through a molten bath to separate the pure aluminum metal. Since the electrolytic reduction of alumina requires immense and continuous inputs of electrical power, the location of global smelting facilities was dictated by the availability of cheap electricity rather than proximity to raw bauxite or end-use consumer markets. Consequently, the industrialized nations of the global north, which were generally poorly endowed with bauxite reserves, hosted the vast majority of the world's refining and smelting capacity. In 1972, over 45% of global alumina production was concentrated in the United States, Japan, Canada, France, and Germany. To feed these northern smelters, the industry relied on a vast maritime trade network that extracted raw bauxite from tropical nations in the global south. Following the Second World War, bauxite extraction was heavily concentrated in the Caribbean basin. Alcan drew massive quantities of its ore from British Guyana, shipping it north to be refined and smelted in Quebec. Alcoa drew heavily from operations in Suriname and domestic mines in Arkansas to feed its refineries in East St. Louis and smelters across the United States. Jamaica quickly emerged as the epicenter of Caribbean bauxite extraction. Commercial mining commenced there in 1952, and by 1958, Jamaica was the undisputed leading producer of bauxite in the world, a position it held firmly until overtaken by Australia in 1971. In 1972, the global bauxite market was overwhelmingly concentrated, with Australia accounting for 20%, Jamaica for 18%, Suriname for 11%, and the USSR for 10%. As the era progressed into the 1960s and 1970s, West African nations emerged as increasingly central figures. Guinea, holding an estimated 24% of the world's bauxite deposits, began major industrialization of its mining sector in the 1960s. The formation of the Compagnie des Bauxites de Guinée cemented Guinea's role as a dominant force in global exports. By the end of the 1970s, Guinea had drawn ahead of Jamaica in total production. This bifurcated global supply chain created deep structural inequalities and immense geopolitical friction. The vertically integrated structure of the six majors meant that there was no genuine open market for raw bauxite. The price of the ore was artificially determined by internal corporate transfer pricing mechanisms. This system ensured that the companies could minimize their local tax liabilities in the host countries and concentrate vast profits in the global north. The formation of the International Bauxite Association. The inherent economic tensions of this unequal supply chain reached a breaking point in the early 1970s. Inspired by the geopolitical success of OPEC, Several bauxite-rich developing nations realized the potential of raw materials power and attempted to assert sovereignty over their natural resources by forming a commodity cartel. In 1974, a coalition of producing nations, including Jamaica, Suriname, Guinea, Guyana, Australia, Sierra Leone, and Yugoslavia, officially established the International Bauxite Association. The explicit objective of the IBA cartel was to coordinate policy, control raw material supplies, counterbalance the immense power of the multinational aluminum corporations, and drastically increase national revenues derived from mining operations. Jamaica led the charge against the corporations by implementing a massive tax levy on bauxite production in 1974. To bypass the artificially low transfer prices set by the corporations, the Jamaican government brilliantly tied the new tax rate directly to the realized market price of finished aluminum ingot. This aggressive legislative maneuver instantly increased Jamaica's bauxite revenues from $25 million in 1973 to an estimated $150 million in 1974. Recognizing the effectiveness of the strategy, other Caribbean and African producers rapidly implemented similar levies, forcing the aluminum majors to absorb massive increases in their raw material costs. The era also saw a wave of economic nationalism, such as the government of Guyana nationalizing the bauxite and alumina subsidiary of Alcan. The economics of smelting and the power of hydroelectricity. While bauxite extraction caused geopolitical turmoil in the tropics, aluminum smelting generated profound economic shifts in the industrial north. Because producing aluminum requires staggeringly large amounts of electricity delivered continuously, the industry naturally migrated to regions with massive hydroelectric capacity. In North America, the industry gravitated heavily toward the Pacific Northwest of the United States and the river systems of Canada. The Columbia River Basin became the primary domestic hub for American aluminum production. The industry was the first major industrial customer of the Bonneville Power Administration, utilizing the enormous quantities of electricity generated by the massive Bonneville and Grand Coulee dams. Over the ensuing decades, the industry expanded to employ approximately 11,000 people in the Pacific Northwest, operating 10 massive smelters that consumed enough power to continuously light 3 modern cities the size of Seattle. This symbiotic relationship provided the incredibly cheap energy that made mass production of affordable aluminum consumer goods mathematically possible. However, the global energy crises of the 1970s devastated the fragile economics of the smelting sector. As geopolitical conflicts drove the price of oil and natural gas to unprecedented heights, the cost of generating electricity skyrocketed globally. Smelters not insulated by long-term hydroelectric contracts found themselves suddenly unprofitable. The era of cheap, boundless energy ended, exposing the deep vulnerability of the 6 majors. The energy shocks triggered a brutal capacity shakeout. The most vulnerable smelters were permanently shuttered, marking the beginning of the slow eradication of the United States' domestic primary aluminum smelting. The collapse of producer pricing and the London Metal Exchange. These dual macroeconomic shocks fundamentally eroded the absolute control the major producers had historically exercised over global aluminum pricing. From 1946 until 1972, the major producers had successfully maintained a rigid, highly controlled producers list price. Under this system, dominant firms coordinated production cutbacks during periods of low macroeconomic demand, artificially managing excess capacity and keeping prices remarkably stable. This sticky pricing system successfully insulated the highly capital-intensive industry from the devastating volatility that typically characterized raw commodity markets. However, regulatory environments were shifting. The European Commission, viewing this cartel-like behavior as a blatant violation of antitrust standards, sought to dismantle the producer pricing system. This sustained regulatory pressure, combined with internal fracturing caused by the bauxite and energy crises, culminated in the introduction of the first official aluminum futures contract on the London Metal Exchange in October 1978. The aluminum majors correctly recognized that an open, transparent exchange would destroy their ability to dictate profit margins and furiously opposed the listing. Their ultimate failure to block the LME listing exposed the inherent fragility of traditional corporate structures in the face of accelerating globalization. The shift to the LME fundamentally altered the market dynamics. Prices were no longer set by corporate fiat, but by global supply, demand, and aggressive financial speculation. Aluminum rapidly transitioned into a highly financialized asset class, instantly doubling the volatility of the metal. This new, unpredictable reality forced the industry to fundamentally rethink its operational strategies, paving the way for the rise of secondary recycling to mitigate risk. The packaging revolution, the war against steel and glass. While the macroeconomic foundations of the industry were experiencing seismic shifts, the commercial front was defined by a ruthless war for the everyday consumer. The most consequential victory for the aluminum industry during the post-war era was the total conquest of the global beverage packaging market, transforming aluminum into an intimate item of daily consumption. In the early 1950s, the consumer beverage market was dominated by heavy, returnable glass bottles and three-piece tin-plated steel cans. Steel cans suffered from significant drawbacks. They required a specialized tool to puncture the lid, imparted a metallic taste to the beverage, and rapidly rusted when discarded, creating a highly visible litter problem. The steel industry, focused on lucrative contracts for heavy infrastructure, largely ignored the complaints of the packaging market, inadvertently leaving a glaring vulnerability. The revolution began with Bill Coors, the former chairman of the Adolph Coors Company. Viewing the traditional steel can as a threat to his beer's quality and an environmental hazard, Coors launched an obsessive initiative to develop an aluminum alternative. Coors invested $10 million in relentless trial and error, navigating a landscape where earlier attempts had failed miserably due to structural weakness. On January 22, 1959, the effort culminated in the debut of the 7-ounce, 2-piece recyclable aluminum beer can. The introduction met fierce resistance from the entrenched steel and glass industries, but the consumer response was undeniable. Aluminum cans chilled significantly faster, maintained carbonation, and featured advanced internal polymer coatings that completely prevented the metal from chemically reacting with the liquid, flawlessly preserving the taste. Ermal Fraze and the invention of the pop top. The ultimate ascendancy of the aluminum can was secured by a critical ergonomic innovation in 1963, the invention of the Easy Open Pop-Top tab by Ermal Fraze. Tinkering to solve the annoyance of forgetting a can opener, Fraze realized that aluminum, unlike brittle steel, was uniquely suited to a self-contained opening mechanism. He discovered that aluminum could be precisely pre-scored to weaken a specific sip hole area, fitted with an integrated pull tab secured by a tiny rivet, allowing the consumer to easily break the seal with a simple pull. Fraze successfully patented his design and partnered closely with Alcoa. Alcoa fastened Fraze's invention to the lids of Iron City beer cans, resulting in a staggering 400% increase in sales for the local brewery. Following success in the beer market, soft drink conglomerates could no longer ignore the shift. By 1967, giants like Coca-Cola and Pepsi heavily invested to convert their massive national distribution networks to accommodate the new metal. The industry rapidly iterated to solve the new litter problem of detached sharp tabs, leading Reynolds Metals to introduce the non-detaching stay-on tab in 1976, which finalized the modern form of the beverage can. The precision engineering of the drawn and ironed can. The economic viability of replacing billions of cheap steel cans with relatively expensive aluminum hinged entirely on a manufacturing breakthrough known as the drawn and ironed process, or D&I. Traditional steel cans were manufactured using a three-piece method with a welded side seam. The aluminum can, by contrast, was a two-piece marvel of precision metalworking that eliminated the side seam entirely, completely removing the weakest point of the pressure vessel and allowing the container to be vastly lighter. The drawn and ironed manufacturing sequence begins with flat aluminum sheet metal fed into a cupping press, which stamps out shallow cups. These cups are fed continuously into a bodymaker machine, where a specialized punch forces the aluminum cup through a series of progressively smaller dies. This ironing phase aggressively stretches and thins the sidewalls of the aluminum cup to roughly 1/3 of the original thickness, while leaving the flat base at its original gauge. To counteract immense internal carbonation pressures, the bottom of the can is drawn inward to form a precise concave dome. This dome arch redistributes internal pressure outward against the thicker base, elegantly utilizing structural geometry to provide massive physical strength with minimal material weight. Finally, the ultra-thin cylinder is trimmed, coated with protective epoxy, decorated and necked inward to accept the lid. Over the ensuing decades, relentless metallurgical optimization allowed manufacturers to continually reduce the gauge of the aluminum sheet required, driving down per-unit costs and achieving unprecedented global economies of scale. The birth of the closed-loop recycling economy. The triumph of the aluminum beverage can inadvertently triggered the creation of the modern closed-loop recycling economy. While the aluminum can was vastly superior to steel, the primary production of virgin aluminum remained exceptionally energy-intensive. As energy crises drove electricity prices to unprecedented heights, relying solely on primary smelting to feed the billions of units demand for packaging became economically unsustainable. Fortunately, aluminum can be melted down and reformed infinitely without any loss of structural integrity or purity. Crucially, secondary production of aluminum, recycling scrap metal, requires merely 5% of the total electrical energy needed to extract and smelt primary aluminum from raw bauxite ore. To capitalize on this massive energy arbitrage, the aluminum majors initiated the construction of a nationwide public recycling infrastructure. In 1970, Coors launched the Cash for Cans program, monetizing consumer behavior by offering a penny per can for the public to return empty containers. The rest of the industry rapidly followed suit, establishing thousands of buyback centers. The growth of the secondary aluminum industry between 1970 and 1990 was phenomenal. By 1989, the quantity of aluminum recovered through secondary smelting surpassed 2 million metric tons annually. The aluminum beverage can rapidly became the most recycled consumer product in the world, with the recycling loop operating so efficiently that a discarded can could be collected, melted, filled, and placed back on a shelf in fewer than 30 days. This booming secondary market deeply insulated the industry from the volatile energy shocks of the late 20th century. Architectural integration, skyscraper facades, and the curtain wall. Concurrent with its conquest of the consumer packaging market, aluminum fundamentally redefined the physical environment of the 20th century city. The post-war economic boom triggered a massive expansion in commercial real estate, providing the aluminum industry with an ideal canvas to demonstrate the structural and aesthetic capabilities of its materials. The integration of aluminum into modern architecture was primarily driven by the widespread adoption of the curtain wall system. Historically, a building's height was limited by the massive weight of its load-bearing masonry walls. The advent of the internal structural steel frame allowed architects to treat the facade as a lightweight envelope suspended entirely from the internal skeleton. Post-war metallurgical advancements made precision extruded aluminum the undisputed material of choice for these high-rise facades. The standard modern aluminum curtain wall consists of a highly engineered geometric grid composed of vertically extruded aluminum mullions and horizontal rails. This lightweight framework spans multiple floors, absorbing lateral wind loads, accommodating thermal expansion, and flexing safely with the natural sway of the skyscraper. The spaces within this grid are filled with architectural glass and opaque horizontal panels known as spandrels, often made of heat-strengthened glass fused with colored ceramic, bringing vibrant colors to the urban skyline. To overcome initial skepticism from the traditional construction industry, major aluminum producers engaged in massive programs of corporate patronage. In 1953, Alcoa completed its 30-story headquarters in Pittsburgh, serving as a monumental advertisement for the metal's capabilities. The Alcoa building's curtain wall was clad entirely in a striking aluminum dress of large stamped panels of anodized aluminum. This daring expression showcased the material's ability to be pressed into complex geometric forms while remaining entirely weatherproof and impervious to thick industrial soot. The Alcoa Forecast Program and the Aesthetics of Aluminum. Recognizing that aluminum needed to capture the cultural imagination, Alcoa aggressively expanded its architectural promotional strategy through its highly influential Forecast campaign, running from 1956 to 1960. The initiative sought to provide the public with a glimpse into the wonderful world of tomorrow, emphasizing the lightness, beauty, and novel applications of aluminum in art, architecture, and interior design. Alcoa commissioned a diverse array of mid-century design luminaries, including Isamu Noguchi, Alexander Girard, and the legendary Charles and Emma Ames. In residential architecture, Alcoa hired modernist architect Charles Goodman to design the Carefree Home, a series of demonstration houses featuring vibrant color-anodized aluminum elements. Another remarkable contribution was the Kaleido-Screen, a functional sculpture designed in 1957 by Herbert Bayer. The Forecast program fundamentally shifted public perception, proving aluminum was a versatile designer's palette capable of capturing the utopian optimism of the space age. The pinnacle of high-rise engineering, the World Trade Center. This potent synthesis of advanced engineering and sleek modernist aesthetics cemented the aluminum curtain wall as the absolute defining feature of the international style of architecture. Ludwig Mies van der Rohe's iconic Seagram building in New York heavily influenced a generation of corporate high-rises. The pinnacle of this era's architectural integration was achieved with the design and construction of the World Trade Center in Lower Manhattan. Lead architect Minoru Yamasaki designed the complex with twin 100-story towers, utilizing an innovative framed tube structure. The towers were designed with extremely narrow office windows, reflecting Yamasaki's desire to make occupants feel highly secure. Crucially, the entire massive exterior perimeter of the World Trade Center towers was sheathed in a gleaming, vertically pinstriped facade of advanced aluminum alloy. The aluminum cladding provided unparalleled protection against the elements, requiring virtually zero exterior maintenance, while perfectly expressing the sheer verticality of the structures. The World Trade Center stood as the ultimate testament to aluminum's incredible strength-to-weight ratio. Automotive evolution, the long road to fuel efficiency. While the architectural and packaging markets embraced aluminum enthusiastically, the American automotive industry proved to be a highly resistant frontier. From the inception of the automobile, visionary engineers recognized the theoretical performance advantages of lightweight metals, with early pioneers like Carl Benz using an aluminum engine in a race car as early as 1901. However, the post-war American automotive industry was built upon the unyielding economics of cheap steel and heavy cast iron. In an era of exceptionally low fuel prices and expanding suburban highways, the premium cost of aluminum relegated the metal to niche applications, mostly reserved for luxury sports cars and high-performance European imports. The paradigm shifted permanently during the geopolitical oil embargoes and energy crises of the 1970s. As fuel prices quadrupled and the federal government aggressively introduced the Corporate Average Fuel Economy (CAFE) standards, Detroit automakers were forced to drastically improve the fuel efficiency of their fleets. The most immediate engineering solution was aggressive vehicle lightweighting. Because 1 kilogram of engineered aluminum could effectively replace up to 2 kilograms of heavy steel or cast iron without sacrificing structural integrity, the metal transitioned almost overnight from an expensive niche luxury to an absolute regulatory and economic necessity. Automakers began systematically replacing massive iron engine blocks, transmission casings, and suspension joints with advanced cast aluminum alternatives. The deep integration of lightweight aluminum V8s drastically reduced the weight over the front axle, profoundly improving vehicle handling dynamics and safety. Over subsequent decades, the use of aluminum steadily expanded, completely reversing decades of unquestioned steel dominance. Military mobility. The M113 Armored Personnel Carrier. This sweeping civilian transition to structural lightweighting was heavily informed by intense military pragmatism developed during the Cold War. The United States military recognized that rapid mobility and air transportability were absolutely paramount. The Army sought a vehicle combining all-terrain capability with airborne deployment, leading to the development of the M113 Armored Personnel Carrier by FMC Corporation, adopted in 1960. The M113 was a truly revolutionary combat vehicle, standing proudly as the first military platform to feature a hull constructed entirely of aluminum armor, utilizing highly durable 5083 aircraft-quality alloy. By using aluminum, the vehicle's gross weight was kept remarkably low, allowing excellent speed and agility. During the intense combat operations of the Vietnam War, the M113 proved extraordinarily successful. The thick aluminum armor protected the crew from small arms fire and shrapnel, while remaining light enough to aggressively break through heavy jungle thickets. The overwhelming operational success of the M113 proved definitively that specialized aluminum alloys could provide ballistic and structural integrity highly comparable to heavy steel. Cold War Aerospace, the jet age and advanced metallurgy. The absolute most technologically demanding arena for aluminum integration between 1945 and 1990 was the aerospace sector, continuously driven by the high-stakes geopolitical pressures of the Cold War. The global aviation industry had relied heavily on aluminum since the First World War, utilizing early copper-alloyed metals like duralumin. However, the advent of the revolutionary jet age in the 1950s introduced entirely new, destructive aerodynamic stresses that pushed traditional metallurgy to its breaking point. Modern jet aircraft flew at significantly higher altitudes, subjecting the aluminum fuselage to extreme cyclical pressurization and the deadly threat of cyclic metal fatigue. Furthermore, the rapid transition to supersonic military and commercial speeds introduced intense thermal friction and massive aerodynamic loads. To meet these existential challenges, the global aluminum industry engaged in massive collaborative research to develop ultra-high-strength, fatigue-resistant alloys. Metallurgists learned to manipulate the microscopic structures of the metal through precise heat treatments and exotic alloying elements, leading to the absolute dominance of the 2000 and 7000 series aluminum alloys. The 2024 alloy became the undisputed industry standard for aircraft skins and tension-loaded components due to its exceptional resistance to fatigue crack growth. For highly critical internal structural frameworks, where absolute rigidity was required, aerospace engineers turned to the 7000 series, specifically the 7075 and 7050 alloys. These highly advanced alloys formed the structural backbone of iconic Cold War aircraft, from the massive Boeing 747 to the supersonic Concorde. The space race, from Sputnik to the Space Shuttle. The absolute culmination of this relentless metallurgical evolution occurred in the hostile vacuum of space. The space race required materials possessing maximum possible strength, minimal weight, and flawless reliability under extreme temperature fluctuations. The era of space exploration was literally forged in aluminum. In 1957, the Soviet Union launched Sputnik 1, constructed from a highly polished aluminum alloy. When NASA engineers subsequently designed the colossal Saturn V super heavy-lift launch vehicle to carry Apollo astronauts to the moon, they unequivocally selected high-strength aluminum alloys as the primary structural materials for the rocket's immense liquid oxygen and fuel tanks. These specific copper-bearing alloys were meticulously chosen because they uniquely retained their structural integrity and ductility at the mind-numbing cryogenic temperatures of liquid oxygen, whereas traditional carbon steels would become highly brittle and catastrophically shatter under launch pressures. The absolute reliance on advanced aluminum extended directly into the Space Shuttle program in the 1980s. The complex structural framework of the orbiter and the highly critical structural interfaces were all heavily dependent on the malleability and immense structural resilience of advanced aluminum alloys. The mastery of aluminum metallurgy achieved by the aerospace industry effectively removed the material limitations on human exploration. Geopolitical supply chain shift and market volatility. The contemporary landscape of the global aluminum market is the direct result of a massive systematic shift in production power from the West to the East, a transition that has fundamentally reshaped pricing dynamics, international trade policies, and domestic industrial strategies worldwide. The era following the mass commercialization of aluminum was characterized primarily by Western dominance, with the United States operating as the undisputed titan of primary production. In the year 1980, the United States accounted for roughly 1/3 of the world's primary aluminum output, producing over 4.65 million tons annually. However, the dawn of the 1990s brought seismic geopolitical shifts that would permanently alter the trajectory of the industry, setting off a chain reaction of market gluts, price collapses, and a wholesale restructuring of the global supply chain. The collapse of the Soviet Union in December 1991 served as the first major watershed event for the modern aluminum market. For decades, the Soviet state had maintained a massive, largely hidden aluminum industry designed specifically to feed its sprawling military-industrial complex. When the political apparatus disintegrated, domestic demand from the Soviet military vanished practically overnight, leaving Russian smelters with mountainous inventories of primary aluminum that the domestic economy was entirely unable to consume. Bereft of state sponsorship and funding from Moscow, individual Russian smelters quickly aligned themselves with aggressive Western commodity trading firms. The resulting outward flow of metal onto the global market was staggering in its volume and speed. In 1989, Soviet aluminum exports stood at a modest 232,000 metric tons. By 1992, exports from the newly formed Russian Federation had nearly quadrupled to 964,000 metric tons. And by 1994, the figure skyrocketed to 2.1 million metric tons. This sudden, unprecedented influx of metal threatened to completely overwhelm the global market outside of China, resulting in a severe supply glut that severely depressed spot prices on the London Metal Exchange, or LME. The crisis reached such acute levels that in early 1994, a coalition of major producing nations, including the United States, Russia, Australia, Canada, and the European community, convened to sign a Memorandum of Understanding. This historic agreement aimed to temporarily reduce global output by up to 2 million tons annually to stabilize the market, with Russia committing to a 500,000-ton reduction in output by the summer of that year. While the 1994 memorandum provided temporary relief, the structural damage to the United States' primary aluminum sector was already well underway, exacerbated by domestic energy policies. Because aluminum smelting is an extraordinarily energy-intensive process relying on the continuous electrolysis of alumina, electricity costs ultimately dictate a smelter's global competitiveness. In regions like the Pacific Northwest, the Bonneville Power Administration began terminating direct service power contracts with aluminum smelters as it struggled to balance rising local retail demand and lucrative opportunities to sell power to the California market. By 2007, the termination of these contracts served as the definitive death blow to the Northwest's once mighty smelting capacity. Consequently, U.S. producers increasingly found it more profitable to shut down their pot lines and sell their contracted electricity back to the grid rather than produce metal in a globally depressed market. As the United States and European producers contracted, the People's Republic of China initiated the most aggressive and sustained industrial expansion in the history of the metals market. In 1990, China was a minor player in the global aluminum landscape. By 2000, it had become the second largest producer, and by 2003, it confidently claimed the top position globally. Today, China produces a staggering 43 million metric tons annually, commanding approximately 60% of total global output. This expansion was not the result of organic free market dynamics, but rather a highly orchestrated state-sponsored industrial strategy. The Chinese government provided pervasive support through a complex matrix of subsidies, cheap capital, and regulatory fast-tracking. An analysis by the Organization for Economic Cooperation and Development estimated that upwards of $70 billion in state subsidies were directed to major Chinese aluminum companies between 2013 and 2017 alone. Furthermore, Beijing facilitated the development of world-class smelting technology by funding major technical universities, which then licensed advanced designs to state-owned enterprises at minimal or no cost. Supported by massive domestic coal reserves that provided artificially cheap electricity and bolstered by an export rebate program that returned the 13% value-added tax to domestic producers, Chinese smelters scaled at warp speed. Permitting and construction projects that would take half a decade to navigate in the West were routinely completed in less than a year, supported by vast infrastructure networks built at no cost to the smelters by state construction entities. However, this rapid expansion has also drawn intense international scrutiny regarding human rights abuses and forced labor within the supply chain. According to comprehensive reports by the United States Department of State and the Department of Labor, there is strong evidence that aluminum production in China is heavily intertwined with state-sponsored labor transfer programs in the Xinjiang Uyghur Autonomous Region. These programs systematically subject Uyghurs, ethnic Kazakhs, and other Muslim minorities to compulsory labor in highly energy-intensive industries, primarily through the smelting of alumina. The revelation that a significant portion of the global aluminum supply is tainted by forced labor has accelerated efforts by Western governments and corporations to audit their supply chains and seek alternative, ethically sourced materials. The downstream economic effects of China's overall expansion were transformative. China did not merely seek to export raw primary ingots. The state rapidly built out massive semi-fabrication and finishing capabilities, allowing it to export millions of tons of high-value extruded and rolled products annually. This systematic oversupply effectively capped global aluminum prices on the London Metal Exchange based on China's low replacement costs, rendering large swaths of Western smelting capacity economically unviable. Between the years 2000 and 2015, the United States saw the permanent closure of nearly 2.7 million metric tons of domestic smelting capacity. Today, the U.S. primary aluminum footprint is a shadow of its former self, with production plummeting to just 670,000 tons in 2024, representing less than 1% of global output. The historical pricing of aluminum reflects these massive macroeconomic shifts and supply shocks. During the industrial boom leading up to 2008, LME aluminum spot prices surged to over $3,000 per metric ton. However, the 2008 global financial crisis triggered a catastrophic collapse in industrial demand, causing prices to plummet below $1,500 per metric ton. Research indicates that the price fluctuations during and immediately after the 2008 crisis were driven almost entirely by economic activity shocks and a lack of demand. In stark contrast, the extreme price volatility experienced during the COVID-19 pandemic and the subsequent 2021 global supply chain crisis, where prices surged back to nearly all-time highs above $3,000 per ton, was driven heavily by supply disruptions, shipping bottlenecks, and massive surges in freight costs. The unchecked expansion of Chinese capacity eventually collided with environmental realities and domestic economic policies. Recognizing the severe environmental degradation caused by coal-fired smelting and the severe economic inefficiencies of massive industrial overcapacity, Beijing instituted a strict 45 million metric ton cap on total primary aluminum production in 2017. As of early 2025, Chinese production hovers at an annualized rate of 44 million tons, pushing capacity utilization to an extreme 98.2% and leaving almost no room for further growth without violating the state-mandated regulatory ceiling. This cap has forced a dramatic geographic migration within China, driving smelters away from the coal-heavy northern provinces toward the abundant hydroelectric resources of Yunnan province and the vast wind and solar installations of Inner Mongolia. The Chinese government now mandates that 30% of national smelter power must be derived from renewable sources by 2027, fundamentally altering the energy profile of the global supply chain. Simultaneously, the geopolitical backlash against Chinese market dominance led to a fracturing of global trade. In the United States, the implementation of Section 232 tariffs on aluminum imports in 2018 served as a blunt but effective instrument to stabilize the domestic market. These tariffs, combined with sweeping anti-dumping and countervailing duties, effectively curtailed the influx of subsidized Chinese extrusions and sheet products, sparking a wave of domestic investment. While primary smelting jobs in the United States have largely vanished, the midstream and downstream sectors, rolling mills, extruders, and secondary recyclers have experienced robust employment recoveries. An economic impact study revealed that the U.S. aluminum industry currently directly employs over 164,000 workers and drives more than $92 billion in direct economic output, supporting nearly 700,000 total jobs when indirect and induced impacts are considered. Jobs in secondary aluminum recycling alone grew by over 12% between 2022 and 2024, reflecting a massive shift toward a circular economy. The most critical evolution in the modern supply chain, however, is the imperative of decarbonization. Primary aluminum production accounts for roughly 3% of global direct industrial greenhouse gas emissions, primarily due to the electricity consumed and the chemical reaction inherent in the 19th century Hall-Héroult smelting process, which utilizes massive blocks of carbon anodes that burn away and release immense volumes of carbon dioxide. In response to strict corporate sustainability goals and international climate accords, the industry is racing toward the commercialization of green aluminum. The vanguard of this technological revolution is Elysis, a joint venture forged in 2018 between industry giants Alcoa and Rio Tinto, supported by massive investments from Apple and the governments of Canada and Quebec. ELYSIS has successfully developed and deployed a proprietary inert anode technology that entirely eliminates direct greenhouse gas emissions from the smelting process. By replacing consumable carbon anodes with advanced chemically inactive composite materials, the ELYSIS cells emit only pure oxygen as a byproduct. Having successfully scaled from pilot plants to commercial-size 450 kiloampere cells operating within existing commercial smelters in Alma, Quebec, this technology represents the first fundamental alteration to aluminum smelting since its invention. When paired with renewable hydroelectricity, inert anode technology offers the promise of a truly zero-carbon primary metal, a development that will define the competitive landscape of the global supply chain in the decades to come. Consumer electronics, the unibody revolution, and premium aesthetics. While the geopolitical struggles over raw aluminum capacity reshaped the macroeconomic landscape, a parallel revolution was occurring in industrial design and consumer culture. Aluminum's transition from a utilitarian commodity used primarily for beverage cans and window frames into an object of high-end consumer desire was driven almost entirely by the technology sector. Prior to the late 1990s, consumer electronics were overwhelmingly encased in injection-molded plastics, chosen for their low manufacturing cost, radio frequency transparency, and ease of mass production. Aluminum was rarely utilized outside of internal heat sinks or structural bracings hidden from the user's view. The initial shift in consumer perception began when Motorola utilized stamped aluminum for its iconic Razr line of cellular phones, proving conclusively that sleek metallic finishes could drive consumer lust. However, it was Apple Incorporated, under the visionary leadership of Steve Jobs and Chief Design Officer Johnny Ive, that would elevate aluminum to the undisputed premium standard of modern technology. Apple's deep infatuation with the metal began with the 2003 PowerBook G4 laptop, which utilized a casing constructed from a complex jigsaw puzzle of stamped sheet aluminum. While a massive aesthetic improvement over the beige, gray, and black plastics of the era, the multi-part assembly required internal skeletons, numerous screws, and plastic gaskets to manage the manufacturing tolerances between the discrete metal pieces. Subsequent products, such as the iPod Mini and early iterations of the iPod Nano, experimented with seamless extruded aluminum shells, but these techniques were strictly limited to small, simple, tubular geometries. The absolute paradigm shift arrived in 2008 with the introduction of the MacBook Unibody design. Apple's engineering team completely reimagined the manufacturing process by abandoning sheet metal stamping in favor of computer numerical control machining, a subtractive manufacturing process previously reserved almost exclusively for low-volume, mission-critical, high-precision aerospace components. Rather than assembling a laptop chassis from dozens of flimsy structural parts, Apple began with a solid 2-inch thick extruded block of raw aluminum. This slab was then subjected to 13 separate, highly calibrated milling operations. The massive CNC machines carved out the internal compartments, the exact placements for the logic board and battery, and precision-cut the keyboard lattice directly from the solid face of the metal. This unibody approach produced a chassis that was fundamentally thinner, drastically lighter, and infinitely more rigid than any preceding design in the history of portable computing. The structural integrity of the single piece of aluminum allowed for the elimination of internal bracing, freeing up precious internal volume for much larger batteries and higher performance components. To execute this level of precision at a massive consumer scale, Apple essentially monopolized the global supply of advanced CNC milling machines, reportedly purchasing 10,000 units to meet their sheer production demands. They further innovated by purchasing the only factory in the world capable of producing specialized laser drills, using them to micro-perforate the aluminum to create invisible sleep indicator lights that shined through the solid metal, as well as precise acoustic speaker grills. The aesthetic language established by these rigorous processes came to define the concept of premium in consumer electronics, Apple deliberately abandoned glossy finishes in favor of a fine matte texture achieved by aggressively blasting the raw machined aluminum with ultra-fine glass beads at high velocities. This texturing was immediately followed by an electrochemical anodization process that thickened the natural oxide layer of the metal, protecting it from corrosion while allowing it to be dyed in a sophisticated jewelry-inspired palette of metallic hues, ranging from space gray to rose gold. As the unibody philosophy migrated from laptops to smartphones, the specific metallurgical properties of the aluminum became a point of intense engineering focus and intense public scrutiny. For years, the industry standard for device enclosures was 6000 series aluminum, an alloy primarily featuring magnesium and silicon. The 6000 series, specifically variations like the 6063 alloy, offered excellent thermal conductivity at 200 watts per meter Kelvin, exceptional corrosion resistance, and was highly malleable, making it ideal for the extrusion and high-speed CNC machining processes. However, the relentless drive to make smartphones as thin as technologically possible eventually exposed the structural limitations of the 6000 series. In 2014, the release of the exceptionally thin iPhone 6 Plus resulted in a widespread public relations crisis, colloquially known as Bendgate, where users found their devices permanently warping under the mechanical stress of being kept in tight pockets. Apple's initial strategic plan to bypass aluminum altogether and create unibody enclosures entirely out of ultra-hard synthetic sapphire crystal collapsed disastrously when their exclusive supplier, GT Advanced Technologies, failed to achieve the necessary production yields and quickly filed for bankruptcy. Forced to rely on aluminum, but requiring vastly superior structural strength, Apple pivoted aggressively to 7000 series aluminum for the subsequent iPhone 6s and the original Apple Watch Sport models. The 7000 series alloys are heavily alloyed with zinc, a complex metallurgical combination traditionally utilized in aerospace applications and high-performance competition bicycles. The addition of zinc, often paired with magnesium, yields an alloy that is significantly harder and boasts a tensile strength up to 60% greater than standard 6000 series aluminum. While this thoroughly solved the structural vulnerabilities, effectively rendering the iPhone 6s impervious to casual bending, the 7000 series was notoriously difficult to machine, could not be easily extruded, and posed severe chemical challenges for achieving consistent color anodization across massive production batches. Apple's ability to domesticate 7000 series aluminum for mass production underscored the extreme lengths to which consumer technology companies were willing to push material science in the pursuit of perfection. The unibody aluminum aesthetic pioneered by Apple rapidly became the inescapable standard across the entire consumer electronics ecosystem. Competitors who had long defended the durability and radio transparency of polycarbonate plastics were eventually forced to capitulate to undeniable consumer demands for premium materials. By 2015, Samsung abandoned its plastic heritage with the launch of the Galaxy S6, embracing an aluminum frame and glass sandwich design that clearly signaled its entry into the ultra-premium tier. Microsoft similarly embraced the CNC machined aluminum and magnesium aesthetic for its Surface line of hardware. From the original 2007 Surface Table to the critically acclaimed Surface Book with its high-resolution Pixel Sense display, and even experimental dual-screen devices like the Surface Duo and Neo, Microsoft relied heavily on the cold, precise feel of the metal to communicate engineering superiority and justify high price points. Today, the narrative surrounding aluminum in consumer electronics has shifted drastically from structural engineering to environmental sustainability. The sheer volume of electronics produced annually places immense strain on primary resource extraction and generates massive carbon footprints. Recognizing that recycling aluminum requires only 5% of the energy needed to smelt primary metal, technology giants have aggressively engineered their supply chains to support a circular economy. Apple currently utilizes 100% recycled aluminum for the enclosures of its MacBooks, iPads, and Apple Watches, capturing high-quality scrap from its own manufacturing lines and utilizing innovative material recovery robots like TAZ to extract materials from end-of-life electronics. Products like the MacBook Air currently feature up to 55% total recycled content across all components. Samsung has heavily followed suit, integrating both pre-consumer and post-consumer recycled aluminum into the structural frames and internal components of its flagship Galaxy S24 and S25 series devices, alongside recycled cobalt and rare earth metals. This massive transition to recycled aluminum is not merely a public relations exercise. It is a critical mathematical component in these corporations' efforts to avoid millions of tons of Scope 3 greenhouse gas emissions and reach ambitious net-zero carbon targets by 2030. Advanced mobility and the electric vehicle era, the physics of lightweighting. If the consumer electronics sector transformed the public perception of aluminum, the global automotive industry has transformed its ultimate scale and utility. The modern era of vehicle manufacturing is characterized by an existential, relentless war against weight, a battle in which advanced aluminum alloys serve as the primary weapon. While internal combustion engine vehicles have gradually adopted aluminum for engine blocks, cylinder heads, and wheels over the last 30 years to meet rising fuel economy standards, the massive industry-wide transition to battery electric vehicles has initiated an absolute golden age for automotive aluminum. This surge is driven entirely by the inescapable physics of energy density and the compelling economics of lightweighting. The fundamental engineering challenge of the modern electric vehicle is the lithium-ion battery pack. To achieve the long driving ranges demanded by consumers and necessary to alleviate range anxiety, automakers must install massive battery arrays that frequently weigh between 668 and 3,000 pounds. This immense weight incurs severe thermodynamic and mechanical penalties. The physics of vehicle dynamics dictate that the energy required to accelerate a vehicle, known as inertial force, and the energy constantly lost to the physical deformation of the vehicle's tires against the road surface, known as rolling resistance, are directly proportional to the vehicle's total mass. Rolling resistance alone is approximately equivalent to perpetually driving a vehicle up a 1 in 100 gradient hill. Extensive empirical studies and physics-based modeling confirm that a 10% reduction in overall vehicle weight yields a 6 to 8% improvement in overall energy efficiency. However, the benefits of removing weight from a vehicle are not merely linear, they are highly multiplicative due to an engineering phenomenon known as mass decompounding, or secondary mass savings. When engineers utilize aluminum to reduce the weight of the vehicle's primary structural skeleton, the body in white, they trigger a powerful cascade of secondary weight reductions throughout the vehicle's architecture. A significantly lighter chassis requires smaller, lighter brakes to bring it to a stop. It requires a lighter suspension system to safely support it, and it requires a smaller, lighter electric motor to achieve the exact same acceleration profile. Studies conducted by the Massachusetts Institute of Technology indicate that during a blank sheet vehicle design process, every single pound of primary weight saved in structural, load-bearing components can yield nearly an additional pound of secondary mass savings across the auxiliary subsystems, essentially providing automakers with a 2-for-1 mass reduction deal. In the specific context of expensive battery electric vehicles, the economics of this light weighting are highly compelling. A comprehensive study by FEV Consulting analyzed the precise cost dynamics of substituting heavy traditional steel with aluminum across several different vehicle classes. The study revealed conclusively that aluminum light weighting is immensely profitable because the cost of removing weight using aluminum is significantly cheaper than the cost of adding more battery cells to achieve the exact same driving range. For a small city vehicle, achieving a 28% aluminum content by 2030 is projected to save approximately $74 per vehicle, with the cost of weight saved averaging just $3.14 per kilogram. For a family crossover vehicle, replacing steel with aluminum to reach 42% aluminum content saves approximately $76 per vehicle. For large pickup trucks, hitting 50% aluminum content yields savings of up to $102 per vehicle. By aggressively utilizing aluminum in crash management systems, heavy battery enclosures, and suspension subframes, automakers are able to shave hundreds of kilograms off the vehicle. This massive weight reduction allows manufacturers to fundamentally downsize the highly expensive battery pack without compromising the advertised driving range, ultimately resulting in a net decrease in the total cost of manufacturing the vehicle and drastically improving fleet-wide efficiency. As the automotive industry scaled up its use of aluminum to achieve these goals, it quickly encountered a critical bottleneck: the immense complexity of traditional manufacturing. A conventional automobile chassis is an incredibly complex assembly comprising hundreds of individually stamped steel and aluminum parts, which must be painstakingly joined together on massive assembly lines, utilizing thousands of precise spot welds, rivets, and advanced structural adhesives. This multi-part assembly process is highly capital-intensive, slow, and constantly prone to dimensional deviations over time. To solve this intractable problem, Tesla spearheaded a radical manufacturing disruption known as gigacasting or megacasting. Leveraging ultra-large, high-pressure die-casting machines supplied by companies like IDRA and the Buehler Group, which are capable of generating immense locking forces between 6,000 and 9,000 tons, automakers can now cast entire front or rear vehicle underbodies as a single massive piece of aluminum in a matter of seconds. The manufacturing efficiency gains are staggering. By transitioning to a gigacast rear underbody for the popular Model Y, Tesla successfully eliminated the need to individually manufacture and assemble over 70 individual metal components and cut out over 1,600 robotic welds, condensing the entire structural subsection into one robust aluminum casting. This extreme consolidation drastically reduced the physical footprint of the factory, accelerated production times exponentially, and contributed directly to a massive 147% increase in Tesla's gross manufacturing margins by early 2022, effectively lowering the cost of the Model Y rear assembly by 40%. The undeniable success of this methodology has forced legacy automakers worldwide, including Volvo, Ford, and Hyundai, to rapidly invest in their own gigacasting architectures to remain competitive. The transition to gigacasting, however, presents extreme metallurgical and thermodynamic challenges that required entirely new classes of aluminum. Pushing 80 to 100 kilograms of molten aluminum into a massive, highly complex steel die in mere milliseconds requires alloys with exceptional fluidity and strict behavioral characteristics. Historically, high-integrity aluminum castings utilized in automotive powertrains required intensive solution heat treatments and subsequent water quenching, known as the T6 temper, to achieve the necessary mechanical strength and ductility. In the context of gigacastings, traditional heat treatment is physically impossible. The intense thermal shock of rapidly quenching a component the size of an entire vehicle underbody, which contains highly variable wall thicknesses ranging from thin 2mm ribs to thick structural nodes, would result in catastrophic dimensional distortion and warping, rendering the part useless. Manual or even robotic straightening of such a massive, rigid component is economically unviable at production speeds. Therefore, the industry had to rapidly develop highly specialized proprietary aluminum alloys that can achieve their required strength directly out of the cast without the need for solution heat treatments, relying only on natural or artificial aging, the T5 temper. These novel alloys, typically variations of the Al10 SiMnMg family, heavily rely on incredibly precise chemical tuning at the atomic level. For example, to integrate high volumes of recycled aluminum scrap, which inherently contains elevated levels of iron impurities, metallurgists must carefully increase the manganese content of the melt. The introduction of manganese alters the crystallization of the iron during the rapid cooling process, transforming brittle, needle-like iron silicon phases into more compact, rounded morphologies that do not compromise the ductility or crashworthiness of the final vehicle frame. Maintaining an exact manganese-to-iron ratio is critical to prevent the formation of sludge factors within the alloy. These highly engineered no-heat-treat alloys are the invisible technological linchpin that makes the gigacasting revolution possible, ensuring that the vehicles of the future are lighter, safer, and drastically cheaper to produce. Advanced techniques like Rio casting, which casts aluminum in a semi-solid state, are currently being developed to further push the boundaries of how thin and complex these massive aluminum structures can become. Next-generation aerospace, space exploration, and renewable infrastructure. The aerospace sector has long served as the ultimate crucible for the most advanced aluminum research, demanding materials that can reliably withstand extreme thermal gradients, profound mechanical stress, and relentless pressurization fatigue cycles over decades of service. While the automotive industry focuses heavily on high-volume die casting, aerospace engineering has spent the last 30 years refining the atomic structure of wrought aluminum and hybridizing it with exotic composite materials to push the boundaries of flight. For decades, the standard aircraft fuselage and wing structures were constructed from monolithic 2000 series and 7000 series aluminum. However, the introduction of carbon fiber reinforced polymers threatened to render aluminum obsolete in commercial aviation due to carbon fiber's superior weight savings. To aggressively maintain competitiveness against composites, the metallurgical industry commercialized a new generation of aluminum lithium alloys. Lithium is the lightest elemental metal in existence. By carefully alloying trace amounts of lithium, typically up to 2.45% by mass, alongside copper and zirconium into an aluminum matrix, metallurgists achieved a profound double benefit. The addition of lithium simultaneously reduces the overall density of the alloy, while significantly increasing its elastic modulus, or stiffness. This means aircraft designers can utilize thinner, lighter structural members that exhibit superior resistance to bending and fatigue compared to traditional aluminum. Modern aluminum lithium alloys, such as the 2099, 2196, and 2198 designations, are now essential non-negotiable components of the contemporary aerospace supply chain. They are heavily utilized in the complex internal fuselage structures and extruded crossbeams of the Boeing 787 Dreamliner, the massive fuselage skins of the Airbus A350 XWB, and the heavy load-bearing floor structures of the A380. In private space exploration, aluminum lithium alloys were critical to the development of the SpaceX Falcon 9 rocket, forming the super-chilled cryogenic propellant tanks, where the material's high strength-to-weight ratio directly translated into increased orbital payload capacities and fuel efficiency. Furthermore, the rapidly expanding Chinese domestic aerospace sector has heavily integrated aluminum lithium into the C919 commercial airliner, utilizing the advanced alloy for more than 20% of the fuselage to dramatically enhance fuel efficiency and compete with Western manufacturers. Simultaneous to the development of aluminum lithium, aerospace engineers sought to directly bridge the gap between traditional metals and modern composites by creating hybrid materials. The most successful iteration of this pursuit is the fiber metal laminate, specifically a material known as GLARE, which stands for Glass Laminate Aluminum Reinforced Epoxy. GLARE is an incredibly advanced composite material consisting of multiple ultra-thin layers of aerospace-grade aluminum interspersed with layers of S2 glass fiber prepreg, all bonded together under intense high pressure and heat within autoclaves using epoxy resins. The brilliant engineering behind GLARE relies entirely on the distinct properties of its constituent parts acting in synergy. When subjected to the repeated pressurization and depressurization cycles of commercial flight, monolithic aluminum is highly susceptible to microscopic fatigue cracking over time. In a glare panel, if a microscopic fatigue crack initiates within one of the aluminum layers, the unbroken glass fibers physically bridge the fissure, absorbing the mechanical stress and dramatically retarding the crack's propagation. Beyond this unparalleled fatigue resistance, glare possesses a specific density nearly 10% lower than standard aluminum, exhibits supreme corrosion resistance due to the epoxy matrix, and provides extraordinary fire containment properties due to the exceptionally high melting point of the glass fibers, effectively containing cabin fires better than solid metal. Entering major commercial service in 2007, glare is extensively utilized in the massive upper fuselage skins and tail leading edges of the Airbus A380, allowing the super jumbo jet to achieve structural safety margins that would be mathematically impossible with traditional sheet metal. Furthermore, because its outer layers are standard metal, glare can be assembled, repaired, and inspected using conventional aviation metalworking techniques, successfully avoiding the incredibly costly and complex maintenance procedures typically associated with pure carbon fiber structures. Despite aluminum's absolute dominance in aerospace, the most ambitious space exploration program of the 21st century provided a fascinating counter-narrative regarding the limitations of the metal. When Elon Musk and SpaceX began developing the Starship, a fully reusable super heavy-lift launch vehicle designed for interplanetary colonization of Mars, the initial designs relied heavily on the advanced carbon fiber composites and the aluminum-lithium alloys successfully utilized on their Falcon 9 rockets. However, in a shocking pivot that reverberated through the global aerospace materials sector, SpaceX entirely abandoned both carbon fiber and aluminum-lithium in favor of an optimized, mundane 300 series 304L cold-rolled stainless steel. The rationale behind this unprecedented decision highlights the specific operational boundaries of aluminum. First, Starship must hold thousands of tons of cryogenic liquid oxygen and liquid methane, while carbon fiber becomes dangerously brittle and prone to microfractures at deep cryogenic temperatures, and aluminum-lithium requires highly demanding friction stir welding to maintain structural integrity. Stainless steel actually experiences a massive increase in its strength and ductility at cryogenic levels, completely preventing fracture. Secondly, the vehicle must survive the blistering thermodynamics of atmospheric re-entry. Aluminum alloys possess a relatively low melting point, meaning an aluminum-hulled spacecraft requires incredibly thick, heavy layers of thermal protection tiles across its entire surface to prevent the chassis from disintegrating under the plasma heat. Stainless steel's significantly higher melting point allowed SpaceX to drastically reduce the required thermal shielding on the leeward side of the rocket, completely offsetting the fact that steel is inherently denser and heavier than aluminum at room temperature. Finally, the economic disparity was undeniable. The proprietary aluminum, lithium, and carbon fiber composites were astronomically expensive and incredibly slow to cure in massive autoclaves, whereas raw stainless steel could be procured for roughly $4 a kilogram and welded quickly in open-air environments at their Texas facility. The Starship anomaly serves as a powerful reminder that material selection is never absolute. It is a constant, ongoing negotiation between physics, manufacturing velocity, and ultimate financial cost. Beyond aerospace and mobility, the future of the aluminum industry is inextricably linked to the global rollout of renewable energy infrastructure. According to a comprehensive 2020 study conducted by the World Bank, aluminum is the single most widely used mineral material in the entire solar photovoltaic energy sector. The metal accounts for a staggering 85% of the total mineral material demand for solar components. The high malleability and corrosion resistance of extruded aluminum make it the only logical choice for the millions of miles of solar panel frames required globally, while highly reflective embedded aluminum studs are increasingly utilized directly within the solar cells to significantly increase energy capture efficiency. As global solar capacity continues to expand at record rates, outpacing coal generation additions, the demand for extruded aluminum will scale proportionally, further embedding the metal into the foundation of the post-carbon world. The story of the global aluminum industry from 1990 to the present is a profound testament to the metal's extraordinary adaptability and the relentless ingenuity of modern engineering. What began the era facing an existential crisis from post-Soviet market dumping and the rapid state-subsidized rise of Chinese manufacturing hegemony has emerged as the absolute cornerstone of the modern technological, automotive, and green energy economies. The industry's geopolitical center of gravity has permanently shifted, creating a highly fragmented landscape where Western producers, no longer able to compete on raw primary volume, have aggressively retreated up the value chain into high-tech secondary recycling, advanced downstream extrusion, and the ambitious pursuit of zero-carbon smelting technologies like the ELYXIS inert anode. Simultaneously, the manufacturing revolutions sparked by Apple's CNC-machined Unibody enclosures and Tesla's monolithic gigacastings have proven definitively that aluminum's potential is limited only by the imagination of industrial engineers and the constraints of physics. As the global economy rapidly accelerates its necessary transition away from fossil fuels, the massive demand for aluminum, driven by the insatiable need for lighter electric vehicles, vast solar panel arrays, and infinitely recyclable consumer goods, will only compound. Ultimately, aluminum has transcended its historical role as merely a structural commodity. It is the fundamental physical medium through which the sustainable, electrified future is actively being forged.